Okay, so in this video, we're going to go over the solution to the longest palindrome problem. The longest palindromic substring within a string is the problem definition. You've probably seen this problem before. And so we're going to go over the recursive solution to this so that you can understand how to transform this into the iterative solution for this by looking at the inputs and outputs that the recursive calls make. And that's usually how you're going to actually solve this problem. Okay, so let's look at this code run. So the way that we've defined this is we have our longest palindrome kind of driver function that you pass in the string to, and the string's called s. And then we have our function that will recurse over the string to find all of the permutations of the palindrome, or the possible palindromes that we can find. And it's called f. When we call f of s for the first time, we're going to actually pass in the length of s minus 1, so the last addressable element in the string. And we're also going to pass in length of 1. What this will return to us is the length of our palindrome and a start index. Now, what happens when we recurse through it, though, is that we're actually passing in a start index and the length. So we're passing it in like this, start length. Okay, so let's look at this. Basically, so we'll call it on A, B, C, B, D, O, T, 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 or O, O, T, 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 O, 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 or sorry, O, O, there. So this second palindrome is the largest palindrome that is in the string, but there's another palindrome, B, C, B. So we can kind of see the way that this gets called. Okay, so we'll call our function for the first time. We define the function, and then we call it. We call f on the length of s minus 1, right? And we'll start with all the things of length 1. Now, the way that this works is first we have our base cases. So we open up a whole another stack frame for a smaller, or for a different starting position, but still of length 1. And we'll do this for every element in the string, basically. Let's see, 3. There we go. Okay, so what you can see here is that we've opened up a stack frame for every starting position in the string. And what we're going to do is build out from every starting position in the string. We're going to check to see symmetrical palindromes, as in it's palindromes that are even length, so the middle letter is not present, so like AA. And then we're also going to check for odd length palindromes that are like BCB, where there's a middle letter and then the outer letters are what are symmetrical. So we've opened up every single stack frame. And so now we're actually going to start processing things. So once our length is less than 2 and our start's greater than 0, and so this happened with this. Our length is less than 2, and our start is not greater than 0. So the first time that's happened, we set this length 1 variable to -1, -1. We're going to check a bunch of other things with recursive function calls. So we're going to kind of branch out from each possible starting position. So you can kind of see these as like the first level of nodes in the tree of function calls, right? Each one of these starting positions we're going to explore out. And so then at the end, what we're going to do is return the largest start and length position. So start being, or the length comes first out, and then the starting position comes second. So the length is our greatest digit, or our highest value digit. And so the longer the palindrome, the larger the tuple will be that gets returned. And so then we'll use this max function, which will compare both elements in the tuple as though it's a two-digit number, and it'll return the largest one. So the next thing that we do is we compare, if length is less than 2 and start is greater than 0. So we're sort of filtering out the base case here. And once we filter that out, what we really start doing is comparing, and this is sort of the two-pointer method of comparing palindromes, where you kind of look at the center and then you expand out like this. So here it's start minus 1, right? And so if start is the 0th element and minus 1 is the same as start, that's kind of checking to see if the first and last element are the same. But we don't pass this check, not because of this second thing, but because of this first thing. Our length is less than 2, and our start is not greater than 0. So we set our length to variable to be none. So we reach the end of that particular tree. And then we're going to check to see if our start is greater than 0 and the start plus the length are less than the length of the string. So this is protecting us against going past the length of the string. So we're not checking, on position 10, length 5, because that would be an out of bounds error. So we protect ourselves from any out of bounds errors here. And then we check to see if start minus 1, and that's why we had that, start's got to be greater than 0 so that we can start minus 1. If start minus 1 is the same as start plus length. So when our length is longer than 1, it's 2 corners of a substring. And so the start and the end character have to be the same in order for it to be a palindrome, right? And when we verify that a 2-character palindrome is valid, then we kind of march outward and we validate that that is also valid. Since we already validated this first one, we don't have to validate it again. We can just validate the next largest out. So it's this kind of idea of finding all the centers that could possibly be, and then expanding out from them. So if that's true, which in this first one it isn't, then we move on and we grow. But since it isn't, we're not going to grow. So all of our checks so far have come back negative ones, which means the largest element is length 1, start 0. And so all of our original all of our individual characters, our centers, are palindromes, because one character technically is a palindrome. But we kind of don't care a lot about those. And so if we never found any palindrome in this, we would want to return basically the first character. So right now we're looking at the max and comparing all of those. And what we'll return is this one. It's the largest number. It's 10, essentially. So having come out of that call for start of 0 at length 1, let me just make sure that was what it was. Having come out of the call at start of 0 and length 1, we're now in the start at 1 of length 1. So now we're going to try the first character and we're going to compare it to the character right next to it. And then we're going to expand outward if that's the case, if that works. But in this one, that character is B here. So next thing that we'll do is we'll check to see if B and C are the same. And we do that here. They're not, so we'll return -1, -1 into that length 2 variable. And then we're also going to check to see if B is the middle, are A and C the same? And they're not, so we're going to return -1, -1. So we'll return that length start 1, 1, and that's the largest one, so we'll return 1, 1 out of that call. So now we've gotten rid of start position 0 and start position 1 as valid places to find the largest palindrome. So we'll do the same thing here. And it looks like, wait, go back. it looks like since our start is 2 and our length is 1, start's greater than 0. This, we're not outside the bounds of the string. And so now we can say if 2, that's C, if 2 minus 1, so that's B now, is the same as start plus length. So start is 2, so we're starting here, plus the probable length, so that's this character. So now we're comparing B and B, and those are the same. So we're going to recurse down again, right? So now we're about to call F again with basically we're going to say, okay, well, start position is here now, -1, and then length is, start is, there now, and then length is actually going to be +2. So we're kind of going out by 1 on each side. So now we check that. That's our base case, so we're not at our base thing, and so we're sort of ignoring that. And now there's that, and so our current slice 3,1 is the largest. And we only opened this function call up because we knew that this function call was a palindrome. That happened here because we validated it before, right? When we were looking at start at 2 and length 1, we validated that actually start of 3 is that start of 3 and length 1, or length 3 and start of 1 are valid palindromes. So let's look at this. Oh, geez. There it is. Okay. So now we'll return the max of that, and that's 3,1. So we return the current slice by default because we know that by opening up that stack frame, we found a palindrome. And then if we don't actually successfully open up any other stack frame, so if any of these if statements go through, we'll open up another stack frame. But if we don't, we'll basically just return this current slice, and because we know that this current slice is a valid palindrome. So we return that, and that's 3,1. And so now we're back in the 2,1 function call. But 3,1 is bigger than 2,1. So length 3 at starting place 1 is larger, and so it'll win in this max function. So that's kind of how this works, right? And we can see that this, it gets called a bunch of different times to kind of validate each one of these centers, right? With the largest thing escaping the function call each time. So after the max gets called, we're left with 3,1. So now we're going to compare the starting point of 4 with length 1 and see if we can expand from there. And so we don't, but then we'll start to get to the point where, current slice. Let's see, we're at 3,1 and now we're at start of 5. And if we look, this big second thing starts at 0, 1, 2, 3, 4, 5. And so this one, 5 of length 1, should open up more palindrome or more function calls. So here's where it will happen. Let's see. We know that the current slice is 1. So this is length 1, starting place 5. And so here's where we'll actually start looking at properly this 5, 2, right? So we looked at 1. We compared like palindromes of length 1. But in 6, where we check on start -1, that's position 5, and start, basically we check at 6 and we say if the letter right before us is the same as us, then there might be a palindrome going that direction. So we open up this function call here, and then now we're in this function call, and so length 2 doesn't give us anything, but here it does. So start -1 and starts at 5 and length is 2 is equal to start plus length, and that's not valid. So let's see, this one, yeah, the current slice is 2 and 5, and that's still smaller than 3, 1. So essentially, we won't really get to the point where we're exploring until we get to this center T, right? Because the other two T's are the same. So let's see, that's going to be in, let's see, if this was 5, 6, 7, 8. So it's going to be 8. So I'll just go through here. It looks like 2, 7 is kind of valid, but not as big as 3, 1. So then, let's see, we're in the thing where it starts at 3. And so now we have one, basically where we've opened up, I miss where it opened things up. Hold on, kind of go back here. This is a long one, so bear with me. Okay, so if the start, which we're seeing is 7, so now we're checking to see start -1, that's 6. And I think we start seeing, let's see, we open up another one because, yeah, it's start -1 and length +2. And so then length goes up to 5. And then we're going to check sort of the ends there. And they're, I don't believe they are the same. Let's see. Start 5, length 7. And so, yeah, let's see. Start 7, start 6, start 5. So we kind of move more towards the center there. And then at some point, we stop expanding and we return this current slice. And the current slice is 7, 5, so it's much larger than 3, 1. And so if we look at 7, that's 0, 1, 2, 3, 4, 5, 6, or sorry, 0, 1, 2, 3, 4, 5, 6, 7. So this is the 7th element. And so palindrome of length 5. 7, 1, 2, oh, let's see. Yeah. So we'll just check this out. So if the start is 5, oh, sorry, the start is 5 here. So this is 5. And then it's length 7. 1, 2, 3, 4, 5, 6, 7. So it found that essentially here. I just want to get to the point where I can show you where it was found. This one's a little tough to wrap your brain around without that. Okay, so yeah, we had to get into the function call for 8. We returned 1, 7. So that's starting point 1, or no, length 1, starting point 7. So that's still not big enough. And so then we have to collapse up to 8, which then allows us to check 7 as our starting point. And then what happens is our starting point goes down because we start moving the center over, or the start point over, and checking basically, we move the start point over and then we say, okay, well then the length goes over, not 1, but 2. So that we're kind of going out the same number like that, right? So then the current slice is 2, 7, and that can escape all those negative 1s. And so then it will keep kind of interrogating this, right? It'll say, okay, well then let's expand it one more. So here we're calling it expanded current slice. Start -1, so it starts at 8. Length +2, so then start 7, and we're going to check a palindrome of length 3. And then we'll do that even larger. We'll be able to expand again once we hit the expansion clause, and that was on this step here. And then so we move the start back 1, and we extend the length 2. And once we find that those are the same, then we'll check start at 5, and then length of 7. And then once we find that that's valid, we will, we'll evaluate that against, all those -1s, and then it will pop out of that function call. So now 6, 5, what got passed in is not what's getting returned. It's length 7, start position 5. So then that is never as large as the current slice, right? So here where current slice got set, that's where we got that value, right? So we had 7, 5, and then we added 5, 6 as the current slice. And then there's expanded current slice. This is winning. So then we keep going through, we check all of those, the largest ones, 7, 5. And so then we pop out of this function call. We go 1 forward, and you see how line 18 was the last one to have run, this one. That's where we expanded out. And then, so now we create our current slice, which was the values that were passed in. And if the values that returned from expanded current slice are larger than the values that were passed in, as in we didn't return -1, -1, then we keep that larger size thing. So then we pop out, and 8, 1 is our current slice, right? Or sorry, 1, 8 is our current slice, which isn't as big as 75. And so then that gets compared, and that all collapses out. And so we still have to go through 10 and 11. We still have to compare them. And so they produce a lot of -1s and their current slice, and then that leaves 1, 9 is the largest one there. And then, as you can see, 10, 2, or 2, 10. It's not, real numbers. It's not like 210. It's 2 and 10. So it compares 7 and 2 and 5 and 10 there. So then then now we're just comparing 7, 5 and 2 and 10. And then, so 7, 5 is our largest candidate, and so we return 7, 5, which is the largest parameter. So I'll include this with the video so that you can walk through it yourself. And then later on, I'll reveal how a dynamic program can be, a dynamic programming solution can come of this. The best way to really evaluate this, though, is if you look at this table. I made a table. And so first we have I'll just use like a check mark here. First, we have all of our starts, and then we have all of our lengths, right? So this one is a palindrome, this one's a palindrome, or no, sorry. All of our length ones are palindromes, right? But they're not our largest palindrome. We want the largest one. And then we find, okay, starting position 2, like 0, no. 1, no. But 2 of length 2, that's not the case, but 2 of length 3 is the case, right? So we found a bunch of palindromes that are kind of like that. Now, if you look at some of the other function calls from before, essentially we found this one that's length 2 at position 10. So that's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it's length 2. So that OO, right? So if you can, while you're running this, just kind of keep a table like this. So at position 10, length 2, we have found one, right? And you'll note that once we found position, I'll go back to when we found that position first. Let's see, we were in 8. We got down to 5, 7. Yeah, there we go. So we found one here, right? We found 3, 1 and 2, 7. So 3, length 3 at position 1, and 2, length 2 at position 7. And then what we did is we looked again, start 7, length 3. And we know that that's a palindrome because we got to it from this if statement. If start, if start -1 is the same as start plus length, right? So start 7, length 3 is 1. So every time we open one up, start 7, length 3, we know that there's another palindrome. So we kind of keep track, right? And then start 6, length 5, we know that's a palindrome. So we can mark that. Sorry, not length. Yeah. Start 6, length. What was it? Start 6, length 5. Right, and then we keep going. We have start 5, length 7. So we found one. Start 5, length 7. And we've validated that all these functions are, or that all these parameters don't result in a call, right? And so they don't result in the palindrome. And so we return that, and that's when we start collapsing again. Now we're at 6, 5, and now we're at 7, 3, and now we're at 8, 1. So we compare all of those, and we end up with the length is 7 and the start index is 5. So basically, this solution doesn't call over and over and over again to revalidate that these are happening. But in the other example, they did, right? In the other example, we had to kind of unroll all the way to the bottom and then go back up and then unroll again, right? Like there were a lot of redundant calls. But in this one, there are fewer redundant calls. And so when I post the dynamic programming solution, you'll note that when you run it through Python Tutor, it actually takes more because it has to explore this entire grid. So dynamic programming really only saves you if you're going to have to explore this grid more than once. So if it's O of 2n, right, that's fine. But if it's not going to be O of 2n, like that was far less operations than O of 2n or O of n squared or anything like that. So it doesn't always pay to use dynamic programming. Sometimes the space cost is more and you're not really saving time. And so when you figure out the dynamic programming solution to this one, you'll note that it takes more steps to actually calculate the answer than this recursive call does. So yeah.